You can start now.
All right. So hello everyone. Very much thanks for letting me present this work. I'm currently working at IITM and NCMRWF. I'm a part of this Monsoon mission group, and so these are my collaborators. You can see. So Surya sir is our program director, and all these contributors have made this presentation possible. So if I just look into what is a monsoon mission, we are like in mission mode, we are trying to improve the monsoon predictability over India. Okay, and this includes from weather to seasonal to climate predictions. So what exactly is needed for improving a forecast, a seasonal forecast or a climate forecast, is you can basically improve the model physics or parameterizations in the model. So suppose you take boundary layer parameterizations, you study using it or using observations, and you come up with some closure for some higher order closure for your momentum equation, right? So you try to put it back into model. Now, sometimes what happens is there are large groups of people who are working on, suppose, atmospheric component of the model. As in IITM, we have certain groups, a large number of groups, so which are working on various aspects of atmospheric model, right? So sometimes what happens is each group is trying to implement their own thing, and the improvements are so large that trying to bring it back to a single model becomes really difficult. So suppose we improved the atmospheric model to a large extent, and then we wanted to introduce it into the coupled model. So what we need to do is not just recode the entire atmospheric model, but we need to code the coupler again based on how many changes have happened into the code, right? So this is a big problem in an institute like IITM, where we are trying to do a lot many concurrent development works. So the solution was to introduce next generation seasonal forecast system, prediction system. And here you can see the difference between the older models. So MMCFS V1 is the older model. And if I just go back here in the slide, you can see this one, MMCFS V1 used to have GFS Eulerian dynamical core, NOVA land surface models. SIS ICE model was a part of MOM4. As a code base, it was a part of MOM4. And it was coupled using a hard-coded coupler. Now, our target was to actually implement all the newer versions of all the major components that are available, right? So we have, instead of MOM4, now we have MOM6. And instead of, so atmospheric model has been seeing a lot of development towards dynamical core, right? So people are moving towards like finer and finer resolution. So our first step was to introduce a semi-Lagrangian framework, so GFS-SL instead of GFS-EL, right? And we have newer version of land surface model, NOVA LSM, NOVA MP. So these are the changes that we want to implement in the model. Now this diagram shows what all has already been done by us. So the green dots, if you see, those are the implemented changes, and the red ones are ongoing. So the last time I presented, we did not have go-kart. In the last few months, we have been working hard on implementing go-kart into the model, and we have successfully implemented the GODAT aerosol model into the MMCFS V2. The results today that I'm showing are not based on go-kart model, because we are still continuing the newer simulations with go-kart model. So the biggest change is the coupling framework. Now you can have any new component and write a wrapper around those components based on the input and output, and just couple it into the model. Okay. So this is, I am not going to go into much details about this, but the previous model used to have two components, ocean and atmosphere, and there was a coupler which used to sit in between them. Now we have the library, which is NOVA Earth Modeling System Library, which can interact with all the components separately using wrappers, right? So you have parent Earth model to which all of them can be coupled. So this is the MMCFS V2 configuration results that I'll be showing today. So instead of GFS Eulerian, we have GFS semi-Lagrangian. In the cumulus parameterizations, we have Arakawa-Schubert-based parameterization, SAS and mu SAS. The atmospheric resolution, although it refers to T574, the resolution is actually the same because it's semi-Lagrangian versus Eulerian. And so in the MOM4, near the tropics, the MOM4 resolution was 0.5 by 0.25. Now we have increased to 0.25 by 0.25. And instead of B grade, Arakawa B grade, we are using Arakawa C grade with scale-aware parameterizations. So you can see the resolution is between the ocean models and is increased from 720 by 410 to 1440 by 1080. Right. The ICE model has also been upgraded from SIS to CIS5. The detail, like all of these are major components, so there will be a lot of improvements. If someone is interested, we can, I can direct them to the respective documentation, and there we can find the changes to individual components. Right. So this is the experimental setup that I'll be showing today. So we have 25 years of simulation from 1998 to 2022. I also have experimental simulations for 2023 and 24. In the ocean model, not just the horizontal resolution, but the vertical resolution has increased from 40 to 75 levels. And all these simulations are based on April initial conditions. And we are using ERA5 to basically verify our simulations. So this is JJS climatology. You can see that near India, it is getting all the major convective centers correctly. Over the tropics also, over the Pacific also, it's getting the equatorial rainfall correctly, all the precipitation centers. Now, if you look at the biases, MMCFS1 had a lot of dry bias over land region. So if you look at Indian region, then your African region and the South American region, there was a lot of dry bias. Now, in the new model, the dry bias across the equatorial region has reduced, over the land has reduced, and over the oceans, the wet bias has reduced. So if you look at the African region, it's almost near zero. Near the American, South American region, it's again almost zero. Near the Pacific, all the red, that is high wet bias, is kind of reduced by a lot. So if you just look over Indian region, the dry bias is reduced from minus 1.34 to 1.04. Now, if you look at the interannual variability of the new model and compare it with the older model, if you look at the dry bias, as I already mentioned, it has gone down from minus 1.34 to 1.04. And if you look at the skill at reproducing these last 25 years, the model skill has improved from 0.55 for GPCP to 0.72. Not just that, the root mean square error has come down from 8.99% to 7%. And if you normalize the root mean square error with the standard deviation of observations, so the model should be, the model's variability, the model should be able to capture the more than the standard deviation, right? So if you normalize with observed standard deviation, the NRMSE should be lesser than 1, right? So the new model MMCFS V2 has NRMSE of 0.82, is substantially better than 1.06. And if you look at the last 25 years, MMCFS V2 could capture last 20 years correctly, while MMCFS V1 could capture 15 years correctly. And the skill, as I already mentioned, 0.72. So this is only till 2022. 23 was an experimental run. So GPCP and IMD had almost minus 5%. MMCFS V1 and V2 both produced the sign correctly, although MMCFS V2 was slightly drier. And so in terms of three major metrics which can be used to evaluate a model, first is the correlation coefficient, right? So MMCFS V2 is also, your curve is the correlation coefficient. It is almost 0.72, which is higher than all the other NMM models. We are comparing here with other NMM models. And the 11 number, it is sitting at 0.72. Not just that, if you look at the standard deviation, so the observed standard deviation over ISMR is 1. So any model should be near 1 if it is trying to reproduce ISMR, right? So 11 is also very near to 1. And if you calculate the NRMSC, it has the least NRMSC of all the other models. So SST is one area where the model is performing, not just performing, it's just producing warmer SSTs. So if you look at the Indian Ocean, MMCFS V1 used to have cold SST bias. Now MMCFS V2 has warm SST bias, at least over the Arabian Sea and Bay of Bengal and the rest of the Pacific. Over the southern Indian Ocean, you have colder SST bias still. Now, we try to look at the reasons for why we are getting a warmer SST bias, and we looked at the ocean heat budget and the ocean mixed layer depth. So what we could find was MMCFS V1 had MMCFS V2 had shallower mixed layer depths over the ocean, right, compared to MMCFS V1. So if you look at the difference, MMCFS V2 minus V1 is all negative, right? Most of the places. This is a large scale explanation. It's not like if you study case to case, it might vary depending on other phenomena. But to show shallower mixed layer, generally, if you give the same amount of QNet, if you do a budget analysis of energy, for the same amount of QNet, the shallower mixed layer will be warmer compared to the deeper mixed layer. We have also compared our simulations with the next generation models from GFDL in ECMWF. So GFDL Sphere is the next version for them, which uses MOM6 as same as the MMCFS V2. In their case, they are using AM4 atmospheric model with finite volume dynamical core. And we have also compared with CEAS5 from ECMWF. Now CEAS5 data, the data available is only till 2019. I think recently the 2020 data is also made available. We'll redo this calculation again. But if you just look at the skill at producing ISMR, you can see GFDL Sphere sits at 0.61 and CEAS5 sits at 0.55, which is same as MMCFS V1, the older model. Now MMCFS V2 is producing 0.71, 0.72, right? And if you look at the other oceanic SST indices, which are shown here in the right panel, you can see Nino 3.4 is reproduced by MMCFS V2 with the highest skill. The West IOD is also better, and Atlantic zonal modes and meridional modes are produced better. And CEAS5 is much better at producing EIOD. And overall, because of improved EIOD all the way till 0.81, it is also producing DMI better. So the correlation is not just the one factor we should look at. We should also look at hit and miss rates. So if you look at this scatter plot, if you consider 10% departure as a defining parameter for extreme events, we had 19 years as normal years in GPCP and 3 excess years, 3 drought years, and total of 6 extreme years. So out of which, if we look at MMCFS V1, it produced 7 false alarms, 2 years it could get right, and V2 was wrong or produced false alarm for 5 of those years, and hit rate was 2. So both of them had similar hit rates, but the false alarm was much higher, was higher for MMCFS V1. If we consider 5% departure for defining the excess and drought years, then obviously we have a less number of normal years, and more number of extreme years. So total extreme was 17 years. And the false alarm is 4 years for MMCFS V1, 2 years for MMCFS V2, and hit rate was higher at 14 for V2 and 10 for V1. Okay, look, now looking at the circulation itself, both, so this is ERA 5 850 hectopascal winds. So both the models are able to reproduce the monsoonal circulation and Pacific circulation. If we look at the biases compared to ERA 5, MMCFS V2 is almost near zero compared to ERA 5 850, whereas MMCFS V1 has weakened easterlies over the southern Indian Ocean, and generally the biases are much more in version 1 compared to version 2. And if we want to take into account 200 hectopascal winds also, we'll look at wind shear. So this figure shows U850 minus U200. And left panel is how the wind shear should look. Both the models are able to reproduce that. But if you look at the biases, MMCFS1 has a lot of bias over Indian region going all the way to ocean in the east, right? Whereas MMCFS V2, if you look at, it's almost near zero, the bias in wind shear. And the zero bias almost extends all the way to Central Pacific. So anything, any teleconnections that ISMR will have with Pacific Ocean should be better represented in MMCFS V2, right? So this is the teleconnection plot. So here I'm plotting ISMR as a point observation compared to all the other tropical SST biases, right? So if you look at observation, the response to Nino 3.4 or El Nino is kind of negative, right? So that's what we expect. The model is MMCFS V1 is also producing negative teleconnection, but the response is much stronger compared to what is happening over the Pacific. Now, what is happening over the West Pacific and ISMR and the Bay of Bengal, the response is much exaggerated in MMCFS V1. So if you then compare it, the V2 with observation, the response is very near to what is observed, right? So the response to Pacific Ocean is milder compared to MMCFS V1. Indian Oceans are also, but if you specifically look at Arabian Sea, this is opposite sign, right? But generally it is much over the Western Pacific and the Pacific Ocean, the response is much better. So if you look at the teleconnections itself in terms of numbers, so the observed is minus 0.64. The MMCFS V1 had a much stronger, as we can see in the figure. It has much stronger minus 0.83, which is kind of reduced to minus 0.75. And both the models have similar skill at reproducing Nino 3.4 at 0.8283. ISMR does not show much of, in terms of East IOD, it does not show much of a correlation, right? Which was much stronger at 0.68 or almost 0.7. It's much stronger at MMCFS V1. So this is reduced in MMCFS V2 as well. Okay, so this was all India average. We are now also looking at how the model is performing regionally. So here I'm showing 5 homogeneous regions over India and the model's performance. So if you can see, JJS mean for all these regions is showing, so we have already seen from 0.54 to 0.72. Even the regional, like central northeast India, we can see improvements. Only over northwest India, the performance is kind of reduced. Otherwise, all the 4 regions, it has shown improvement. Now, why northwest India is showing negative is probably because if you look at this teleconnection, it's not getting the Arabian Sea sign correct. So this is just a hypothesis. We are in the process of testing this. So how does it affect the skill over Northeast India? We have also looked at low pressure systems in the new model. So the left panel GPCP shows the contribution of low pressure systems to the overall rainfall over Indian region. So you can see that near the Maharashtra and Madhya Pradesh region, you have a lot of red, right? And MMCFS V2 is able to reproduce that. MMCFS V1 is precipitate, and the contribution from LPS is mostly over Bay of Bengal. The LPSs should penetrate over land and contribute more towards the rainfall. If you look at quantitatively, then almost 50% of rainfall is coming from LPS systems. So better representation of LPS should improve our skill in the model. Now, Samantha et al. Recently showed that the SST gradients in the, so if you move from southeast to northwest, there's a gradient in SST, right? So they suggested that this gradient is what helps the LPS low pressure systems to propagate over land and go much deeper into the land. So MMCFS V1, you don't see much of that gradient. So I'm talking about very sharp gradient near the land, not like a large gradient over the entire Bay of Bengal. I'm talking about very specific gradients about the Indian land, very near to land. So the MMCFS V2 is able to produce that very sharp gradient near the land. And this reflects in the number of LPS systems also. So if we divide into active and break phases, and just overall, if you can see the low pressure systems penetration. So observations of ERA 5 per se shows that the low pressure systems which are generated near the eastern boundary, Bay of Bengal, they are going all the way through the monsoon core region and giving a lot of contribution to precipitation. MMCFS V1 is mostly concentrated over the Bay of Bengal region where we saw this Bay of Bengal precipitation was happening, the contribution was more, right? And MMCFS V2 is very similar to ERA 5, although the numbers are lesser, but it is able to produce low pressure systems which are propagating all the way towards the western side of India. Now, if you look at the numbers itself, so observed LPS is generally 3 times more than in the active phase compared to break phase. Now, in the reanalysis, we found that the number of LPS in the active phase was 1.7 times that of break phase. MMCFS V1 has that contribution lesser at 1.3 times only. So the active number and break phase numbers are not very different. If you see the numbers, see 48 and 36. So they are not very different. MMCFS V2 was able to produce active to break ratio at 1.6 times. You can see that 69 and 42 LPSs. And generally the clustering itself, if you look, the clustering is much better of LPS in the MMCFS V2. This is experimental simulation for 2024. The reason I say it is experimental is we have not finished all the ensembles yet. We are still in the process of finishing all the ensembles. For operational forecast, we need much more ensembles compared to hindcast. So that's the reason. IMD in the long range forecast, the second report that they produced, they said 106%. They have been maintaining it at 106% for mid-season forecast. Our model is producing 6.9 mm compared to 5.95 climatology. So that is almost like 15% positive, right? And what is observed till now is we are almost near zero, so minus 0.5%. And the right panel also shows SST. So this is older towards our East Pacific. So this is a summary. So new monsoon mission model has been developed here, which has upgraded all the major components. So ice model, ocean model. Recently, in the last few months, we were able to also include the aerosol models, the results of which will be coming out soon. We did a 2019 simulation where we could see a lot of effect of introducing aerosol into the model. So the skill at reproducing the last 25 years is phenomenal at 0.72. Wind shear at 850 has reduced a lot. biases. And yeah, generally, in terms of normalized root mean square error, anomaly correlation coefficient, and standard deviation, the model is performing much better. Yeah, so the biggest improvement in terms of software or the coding part is the introduction of names coupling framework. Now, any group that comes up with a new improved version of any component, we should be able to introduce it into the model easily, in an easier way compared to previously. Thank you.
Thank you, Dr. Deepesh. Any questions?
Yeah. So how different is the cumulus parameterization in CFS? I mean, CFS V1 as compared to CFS V2. Are there any changes in the cumulus parameterization?
So the previous version used SAS and the newer version used new SAS. Now, I'm not very sure about the exact changes, but in one of the recent papers by Surya sir, they had shown that new SAS performs really better compared to the old SAS. So if you look at here, the cumulus parameterization, V1 and V2, there's a change in the SAS scheme. What I think is the difference is they have introduced some scale awareness into the SAS scheme and calling it new SAS. In terms of like the fractional area covered by the cloud and all.
Thank you.
Shall I stop sharing my screen now?
Yes, yes.
Okay.
Hello everyone. So I'll be presenting this recently a preprint that recently came out on Monsoon hysteresis, which reveals atmospheric memory. And this preprint was sent to me by a former colleague, Dilip Naidu. I think some of you will know him. And he told me that he has found something similar in his field observation data of soil carbon. So, this paper deals with the hysteresis of monsoon rainfall. Yeah, the hysteresis has been in literature for quite a long time, and this has been talked about in terms of magnetism. And this small demonstration shows what hysteresis is. If we talk about definition, it is just a phenomena that says that the state of the system depends upon its history. But what it means is we can understand that from this plot from Scheffer and others. So here they have done it in the context of ecological systems. Let's say you have some ecological state, and this state depends upon some kind of conditions. So now this state will also depend upon where the for example, if you are in the upper branch, so all of these are stable solutions, and this dotted line is an unstable solution. If you are in the upper branch, if you move a little, you will stay on the upper branch until this point F2, after which you will suddenly fall to the lower branch. And if you start from the lower branch, you will keep on moving in the lower branch until you arrive at the condition F1, after which you will jump back to the upper branch. So where you start really matters in systems where you have hysteresis. now in the context of climate, we can think of it as solution to simple 0-degree energy balance models. So think of this as a current climate, and and think of x-axis as some parameter, let's say albedo. As we change albedo, our temperature changes, and suddenly you hit a transition point, after which you suddenly drop to a temperature which is much lower than the breathing temperature. So basically you go from present day temperature to a temperature where everything is frozen. It's like a snowball Earth. And then now the important point is, in order to go back to the current day temperature, you will have to move the system much more than earlier. So you have to do a lot of work to go back to the state F1, or you have to tweak the parameter to go back to state F1, and then you can jump directly to the current state. And then the area under this curve is sometimes called as hysteresis. Now, so the paper that I'll be discussing has looked at the hysteresis in Indian monsoon rainfall, and here they plot the rainfall on y-axis and solar insolation on x-axis for the central Indian region. And you can see clearly when the insolation increases as we move to summer season, there is no change in rainfall until, let's say, May, June, and May, and then suddenly you start seeing sharp rise in rainfall. But the decrease in rainfall as the winter approaches is somewhat slower. So this gives you an hysteresis.
This is monthly mean, right?
This is monthly mean, yes. And this is mean over all the years, and the gray zone is individual years. So this is not just seen here, you can see it in different regions. So this is Bay of Bengal, East Asia, and Australia. You see some kind of hysteresis everywhere. And these two spatial maps nicely show what it is. So in April and in August, the solar insolation is almost the same, but you see the stark change in the precipitation in these two things. So I was curious if we can. So this has been done with I think satellite observations and gridded observations. I was curious if we can recover something similar in reanalysis, and to first order we do see very similar behavior in RFI as well. So you see this sharp pickup and then a slower retreat. For I have taken the same box as the office. And okay, there is nothing profound here. This is just the annual evolution of different variables in the Indian monsoon domain. So this is rainfall, and this is that sharp pickup as monsoon approaches, and then you have a slower retreat. And we know that the temperature, surface temperature peaks a month earlier, whereas the solar insolation is slowly going. So what causes this memory in the system? In order to prove that, the authors have used interesting concept of what they call as monsoon planet. So this can be thought of as another step in the hierarchy of climate models, which is, let's say, above exoplanets but below normal atmospheric GCMs. So what is a monsoon planet? So this is their monsoon planet setup. They have ocean up until 10 degrees north, and from 10 till I think the 60 or 70 is north, they have the whole planet covered with land, and that planet is in fact covered with some vegetative land. And after that, they have again ocean and ice on the North Pole. So, so in their model, in their setup, ocean is a simplified ocean, which is just a slab ocean without any transport. So you only have fluxes in the vertical, and then land and atmosphere are also run along with that. So let's just look at one animation of this monsoon planet, and this I have taken from the author's talk from last year's EGU. So clearly, as you see, as the sun moves to the northern hemisphere, the land heats up a lot, and you start seeing a lot of precipitation going in the land region. And then, as winter approaches, the insolation drops down, and again the precipitation will come down. Yeah. So this is just an average for the month of August. Same thing. So you have strong heating of the land, and you have these winds going towards the land because of high temperature and lower pressure. And then this causes precipitation, and you can in fact see a double ITCZ kind of structure in this model for August. So now, in order to negate the theory that this memory of or this hysteresis in rainfall comes because of ocean, what these guys did was they changed the thickness of the slab for that model, and these are results with different slab thicknesses. And you see, in fact, for a shallower slab thickness, so for 50 meters, you have a much larger hysteresis. So hysteresis here will be given by the area which is enclosed in this loop. And you can see for a 50-meter depth, you have a larger area. So with this plot, they argue that this memory does not really come from the memory of the ocean, which is most times the hysteresis or the memory is because of the ocean, because of larger heat capacity of the ocean. But here they argue, since with a shallower depth they get a stronger hysteresis, this probably is not a consequence of ocean memory. And also another important thing to note here is you see a sharp pickup of precipitation. So given here in this D panel, after it hits, so after the water vapor threshold is crossed of 30 kg per meter square. So in this model, this threshold is important. I will show later in one of those figures why. But we can see that the water vapor starts picking up before, but the precipitation picks up only after this threshold is met. And this is what they are attributing their hysteresis to. So this is just one more plot showing again for two same states of upper atmospheric boundary condition, solar insolation on 3rd of April. So here the insolation is somewhere here, and 1st of September. We had the same solar insolation, but if you look at the precipitation response, it's very different. And that is due to how much water vapor you have in your column decides how much precipitation you will get in these two different days. Yeah, so in order to test the atmospheric memory, they designed an interesting experiment again where they have a control run which we just saw, and that was for a slab ocean depth of 50 meters, let's say. And all of these are done again for that same slab depth, but the insolation is in this case suddenly dropped to its minimum value on some day, let's say month 8 and day 1. So on that day, they suddenly decrease their solar insolation to the minimum value, which we get in December 21st, on December 21st. And then they check how their precipitation response looks in these two cases. In this case. So here clearly you can see when you have the solar insolation acting as normal solar insolation, you will get this precipitation response. But if you suddenly shut down solar insolation, you start seeing a decrease, and then there is a lag in this decrease. The precipitation does not shut down immediately. That is because you have the residence of atmospheric water vapor, which also goes down slowly. And since you have this criteria where this threshold is met of 35 kg per meter square, you still keep on getting some precipitation. And once this criteria is, so once the water vapor is below this threshold, then the precipitation stops. So this was for one experiment, and then they did one more experiment where they just changed the month, and you see a similar response, and you see actually a similar time scale on which this decay happens for both water vapor and for precipitation. And this is the plot I was referring to. So here for these 3 months, they have done monsoon rainfall versus fallen water vapor, and you can clearly see this exponential increase in the precipitation with water vapor, which starts somewhere around 35 kg per meter square. So this is the threshold, and once this threshold is met, you will have precipitation, this model. And finally, they did one more experiment to show that there can be 2 stable states depending upon where you reduce the solar insolation or where you start from. So this goes back to our first plot where we have seen that the hysteresis depends upon, or the state of the system depends upon where you start from. Again, so these are the 2 set of experiments. In the first one, you increase your solar insolation and then you keep it constant after 25th March. Whereas in the second one, you increase your solar insolation normally and you keep it constant after 9th of September. So these are the 2 days where the insolation is same, but the water vapor in the atmosphere is very different. And this has consequences as can be seen in these 2 precipitation responses. Clearly, for this case, 25th March, you see the response of precipitation is one where you have very weak precipitation, or you can say like monsoon rainfall is suppressed. Whereas in the case of this experiment, because you had a lot of moisture in the water, a lot of moisture in the atmospheric column, you can still sustain a lot of precipitation if the solar insolation is kept constant. Now, so this was a modeling experiment. Then they used some simple theoretical arguments to show that if you model your atmosphere as 2 columns, one which is on land and one which is on the ocean, and think of the monsoon being driven by this temperature contrast, where the temperature contrast gives you some kind of ageostrophic wind, and you can get a model like this, which is a cubic in precipitation as a function of solar insolation. And they show somehow that, okay, so this is their model, and this is a model with some slight modification where they introduce a delay as well. You are able to capture this hysteresis which is in the observation. But there are issues with this model that has, so that this model works on a feedback of moisture advection. So it's a simple principle. So the ageostrophic winds bring in moisture towards the land. The moisture converges and condenses over the land, which gives you diabatic heating. This diabatic heating then re-strengthens your temperature gradient, which re-strengthens your wind. But and this model has been used to argue that you have abrupt changes in monsoon, and you can in fact have bifurcations in monsoons. But there are issues with the model in its formulation in such a way that it misses out on some key processes. And if you incorporate those key processes, the studies have shown that you will not really see, so you will see a linear behavior of monsoon rainfall to changes in insolation. So that's one caveat that we should keep in mind. Yeah, so that was about that study. And then while I was reading that, I got curious and thought, are there any other studies on hysteresis? So there is one more interesting study that I found, but that deals with a very different parameter, which is the CO2 forcing. And I like the idea that these authors have in this paper, where they do a quantification of the hysteresis in a system. So this is a nice schematic which shows that as CO2 increases, let's say you have variable, it could be temperature or it could be precipitation. How does it change? So you can have multiple cases. You can have, in a simple linear system, you will have CO2 increases, the state of the system increases. And as CO2 decreases, the state of the system decreases with the same rate. So you don't have any resistance here. But you can have different cases where you have rates in increase and decrease being different, and then you will have hysteresis. Or you can have another scenario where the initial state is not met at the end. So you have some irreversibility in your system. So you started at increased CO2, and then when you went back and decreased CO2, you end up in a state which is somewhat different from your initial state. So you have some irreversibility in the system. And these authors have used ramp up, ramp down experiments. So a simple description of these experiments are in this panel plot, where you see the CO2 concentration is kept constant for some time, and then it is increased at some rate for some fixed period of time, and then it is decreased with that same rate for that same fixed period of time, so that you get to the same level. And then it is kept constant for some more. And then to study the differences in the increase and the decrease, they study these two phases, the ramp up phase and the ramp down phase. And let's look at what they observe. So this is surface temperature, and this is the hysteresis. So okay, maybe I should describe what hysteresis is for them. So they compute the hysteresis as the area under this curve. So this hash line is hash area is the hysteresis for them. So they did it. They did this exercise at each grid point, calculated the ramp up rate, ramp down rate, and then the area under that curve. So for surface temperature, you see that you have very large hysteresis in the exotropics. Sorry, here, yeah, in the southern hemisphere. And you have, so these hatched area here are the regions where your initial and the final point are close to each other. So you don't have any irreversibility here, so a lot of irreversibility. And these are different regions. You see, there is some area between the red and the blue, so maybe some hysteresis in the lower temperatures there. And different regions will have different hysteresis. So let's see how it looks for precipitation. And we do see hysteresis in the Indian region as well. And yeah, so the strongest signal is seen in the Eastern Pacific. So based on these two criteria, the hysteresis and the irreversibility, the authors have come up with hotspots of the irreversible changes to increase in CO2. And these are the hotspots in red. So southern hemisphere is one, and then you have Africa, India, and the South America as well. So one thing this study does not do is attribute these changes. They just report. But I thought it was nice to just look at those changes. Yeah, I think that's what.
Yeah.
Written. Yeah. Yeah, 50 meters.
Yeah.
Yeah.
It's 50 meters.
I don't think so. They have done hysteresis calculation for other slab portion depth as well, and they. Yeah, this threshold will vary. Yeah. I think that is there in the supply of the paper. I don't recall exactly, but it is there. I will have to check. I don't recall.
Okay, what I had the 11th 2009 paper. He came after that paper, but right here, and crossed a lot of press coverage. They said India will break it down, billion people will die, and so on. And after that, when both Bose and Ashit published this one, no press coverage. So this is politics.
Yeah.
But I can tell you, he missed a chance. All of you should look at it. The same analysis done through energetic frameworks will reveal much more. It is not solar radiation response market. It is the net radiation. He missed the point totally.
Yeah.
Okay. So all of you can look at it and try understanding it different ways. He missed the whole point. Radiation coming in, of course, every year, no problem. It is how much it reaches the land controls the monsoon. So he missed the point completely on that.
Yeah.
But you get a lot of press coverage on there, I can tell you that.
Yeah.
Okay.
Yeah.
Yeah, so I've not talked much about monsoon last few weeks because, this year, after the hiccups of the first month on the onset phase, monsoon has gone very normally, okay? And, all of you know from sports, when the team is winning all the time, we have nothing to say. Everybody is doing well. When the team is doing badly, you criticize one or the other. Same thing is happening here. When the monsoon is based on teamwork, when everything comes together, things go smoothly, and nothing to talk about, okay? But I can tell you, farmers may be happy, but if you're a researcher, you're not happy. Because we learn about monsoon only during failures. Same thing true about your life. Only when failures occur, you learn something. Otherwise, you think you know everything. So this year, nothing to learn so far, except there's one puzzle. Why monsoon is doing so well when La Nina is not going to come? Okay? 3.4 still positive, close to zero. Okay? So that's a mystery. So we are almost 1% above normal. July is 10% above normal, which is not expected. And you see the prediction for this week, it's quite good from NCERP GFS. They showed high monsoon rainfall in North India and no rainfall in South, more or less right. And forecast from both GFS and ECMWF, same thing, North India above normal, South India below normal, all of them are consistent. And you look at Nino 3.4, still hovering above zero. Okay. Now that mystery, which is worth pursuing, if you remember what we discussed this a month back, almost all the models were saying by now, 3.4 should have been negative. All the models did not happen. Okay. Why is that? Now, if you look at the phase diagram of water volume with SST, it should have started coming down rapidly because there's negative energy balance here. Okay. So it should have rapidly come down, but it has not started yet. Now, there are many reasons for it, but I'll show you one interesting reason why this thing is coming. This is what I mentioned earlier, but I want to show it more clearly now. The problem is right along the equator, there are these warm water coming from north, south, north mostly, okay? And so 3.1 is fluctuating, it's not showing decline continuously because of these. These are tropical instability wave. This is not Rossby or Kelvin, it's something very peculiar. It occurs because the gradient is this direction. Okay? Others are driven by what's happening along the equator. This is across. Okay? And this has been studied. A lot of people have looked at it. And it looks better when you don't draw the anomaly. It's much better because warm water here is continuously coming in here, preventing this upwelling water from really coming this far. So this is what is delaying, it will come. At some point, I think it will flip. Okay. And this is the thing which there are a lot of papers published, and we want to look at it. The westward propagating wave from near the equator at the interface between warm and cold. So there has to be a delta T along latitude. Okay. It is there in Atlantic, but easier to see in Pacific. Period is 30 days. Wavelength is 1,000 kilometers. So it will evolve in the next few months, and then finally La Nina will come. Now this is another picture showing all the winds, how the winds bring in warm water from north into the thing. Okay. The matrix waves which occur during this period. Okay, so that's it. So we'll see what happens in subsequent weeks as these waves will die down, and then the real La Nina thing will come over. So what's interesting is if July that was around normal, and I'll talk next week about August. August also everybody is above normal. September may be much above normal because La Nina will really set in at that point. So this is going to be well above normal. And of course, that was partly the forecast in the month of June, but we'll see whether that comes true or not. And I think next week it is Gaurav Srivastava, right? Yeah, we'll meet next week.